Hello once again, class. Welcome to another mock lecture. Today we're going to be tackling inequalities and interval notation. So we're going to get stuck into it here with the number line. Okay. Now the number line is basically just the x-axis, right, of an xy plane. It's a line, so it extends infinitely in both directions, where you've got your positive numbers to the right, your negative numbers to the left of 0, although that doesn't really matter. I mean, you could have a number line, and this is going to be the worst drawing ever, but, maybe the number line starts at 7, right? Maybe it goes to 1,000, right? You could do that if you wanted to, in which case this particular section of the number line doesn't have any negative numbers. But the point is, numbers on the number line ascend from left to right. So if you move left on the number line, your numbers get smaller, and if you move right on the number line, then your numbers get bigger. And it's the relative position between two numbers that we're going to be examining to define inequalities. So the first one we're going to look at is the less than sign. When you say that a number is less than another number, the first number must come before, right, on the number line, the second number. So for example, -4 is less than 3, and the reason that is because -4 is further left on the number line than +3. Right? Same thing we could say with -12 and -1. -12 is much further to the left on the number line than -1. Therefore, -12 is less than -1. Now, this inequality is fine until you start talking about numbers that are on top of each other, like 0 less than 0, right? This is certainly not true. 0 is equal to 0, right? 0 is not further to the left on the number line than itself. It's in the same location. Since we don't want to use an equality, right, because we're talking about inequalities today, and it's certainly not less than itself, we could use the inequality less than or equal to, right? Which is, it's an or statement. So as long as it satisfies one of these conditions, then you can use the less than or equal to sign. And in this case, since 0 is equal to 0, then 0 is certainly less than or equal to, right, 0. In fact, all the examples that we've talked about before this, like -4, which is less than 3, could be -4 less than or equal to 3, right? Because it's satisfying this part of the less than or equal to statement. Same with -12 and -1, right? Those ones could also be described as less than or equal to. So you might wonder why ever use just strictly less than, and it's because that when you're talking about a variable, you know something extra about it when you say that it's strictly less than a specific number. For example, if we're looking at this inequality, right? X is less than 7. X could then be literally any number that is further to the left on the number line than 7. But what we know from this statement is that it can't be 7, right? So visually on the number line, it's this kind of mess of stuff here that I've drawn. Anywhere that's to the left of 7, and generally the convention for visualizing possible solutions for x less than 7 is to basically just kind of highlight the section of the number line that you're working with. Okay, now again, this 7 is not a solution to the inequality x less than 7, but it is a solution to the inequality x less than or equal to 7. And that's what I mean by we know something kind of extra with the strictly less than inequality. Explicitly, what we know is that it's not 7. But here, 7 is now a possibility. In the first one, 6.9999999, right, could be a solution to the inequality x less than 7, but of course 7 can't be. All right, and to distinguish the difference between which inequality that you're visualizing, when you graph this thing, open parentheses is used to denote something that's not equal to, right? Being equal to the number itself, being equal to the upper bound, right, in this case, is not an option, whereas a bracket is used for when it is possible. Okay, and that's the only difference between less than and less than or equal to. It's really one number difference. You can be the upper bound or you can be the lower bound, depending on which way the inequality faces. Okay, and then also a general convention, because this is kind of hard, especially if you're drawing in the same color. Like if I draw a number line and then I'm like, oh, well, here's 7 and I want to represent x less than or equal to 7, and I do this, like it's kind of hard to tell which part of the number line I'm highlighting. So you just move it up, and it makes it a little bit more easier to tell what you're drawing, what you're graphing, what your line graph looks like. This is called a line graph, by the way. Okay. Also, and this is also kind of another thing. Your textbook uses this notation. They use the bracket and the parentheses. I have always used solid dots to represent less than or equal to, or greater than or equal to, basically when your bound can be included, and an open dot when your bound isn't included, right? When it's strictly less than or strictly greater than. That's up to you. I'm not, it's not going to be any difference as far as, oh, you're wrong because you used an open dot or something like that instead of a parentheses. Either one is fine. And I'll probably slip up and use the closed circle and open circle from time to time. But I'll try to be consistent with your book and use the parentheses and the brackets. Okay, so we've got the inequality, -8 less than 0, and that is because -8 shows up further to the left than 0. But we can flip this inequality around, and I used -8 on purpose, because if you literally take this, you got to picture it in your head, and you flip it, you rotate it this way, 180 degrees, you get this, right? 0 is greater than -8. And just like the relationship between the less than or equal to, greater than and greater than or equal to are numbers that are further to the right. So 0 is greater than -8 because it shows up further to the right on the number line than -8 does, right? So there's not much to define here. It's exactly like less than, except instead of being to the left, now your numbers are this number's further right than the second number, right? And it is. 0 is verifiably further to the right on the number line than -8, which makes it greater than. And of course, you could also use greater than or equal to, and the same conventions that we talked about with less than and less than or equal to apply here as well. Okay? Now, before we get into some examples, there is a fifth inequality, and it is the not equal to inequality. In fact, we could say that here. 0 is not equal to -8. Right? But if something's not equal to -8, what that means is that it falls into one of these categories. Right? If something's not equal to something, that means that it's either greater than it or less than it. Right? So we're going to focus on really these four and not so much the not equal to. This particular inequality is really used when you're talking about domains of rational functions, which we might get into much, much later. But for now, let's not worry about the not equal to inequality. Okay, first example that I want to do is I want to graph x greater than 4. We've seen a few examples of how to graph. I think actually just one with the x greater than -7 or x less than 7, whatever it was. Go ahead and pause the video and give it a shot. Try to graph this thing, x greater than 4. You're going to have to decide whether you use a parentheses or a bracket, and also which way the line's pointing. Okay, so hopefully you gave it a think there, and this is what you should get. I used an open parentheses because x is strictly greater than 4. Because x is greater than 4, 4 must be the leftmost number, or x must be somewhere to the right of 4. You can think about it that way. So 4 is the lower bound. 4 is the lower bound of this inequality, and the possibilities for x is anything that's greater than it, but not including, right, 4. Okay, so pretty straightforward stuff. You could also use an open circle as well. Either one of those would be fine. Okay, and then you'd close in the circle if it was x greater than 4, greater than or equal to, or you'd use a bracket if it was greater than or equal to. But since this one's strictly greater than, we got the open parentheses. All right, here's another one, right? Let's say we want to graph x is, so this is two inequalities that we're going to graph. X is greater than -2, but also x is less than or equal to 10. Okay, so let's just kind of, and what I'm going to do is rewrite this inequality, but let's just take this in kind of pieces. X greater than -2. Okay, to me that means -2 has to be the smallest number, right? -2 must be the furthest left of x, and then x could really be anything that's bigger than that, right? And so if we were going to just graph that one piece, we'd have something like this. X is greater than -2, right? So that takes care of this. But then we get this other one. X is less than or equal to 10, which means it can't be bigger than 10. 10 must be now the rightmost number. X has to be somewhere to the left of 10. So X has to be somewhere to the right of -2, but then also somewhere left of 10. So that means we have to stop the line graph somewhere here and kind of get rid of this bit. So it's not an infinite, right, possible solution set here. We're just looking at something that's a small section of the number line. Now, I'm going to put these two things together in what's called a betweenness statement. Again, we talked about the lower bound. The leftmost number is -2. The rightmost number is 10. So those are your lower and upper bounds. So we can combine these two things, and this is called a betweenness statement. So you'd say X is between -2 exclusively, because it does not include -2, but then also -2 and 10 inclusively, right? Because it could include its upper bound. If I just read this thing as a mathematical sentence, you've got -2 less than X less than or equal to 10. But I would actually say X is between -2 exclusively and 10 inclusively. Okay, but again, you're going to get the same graph. It's not including the lower bound. It is including the upper bound. That's why we're using a open parentheses and then a bracket here. And then you just draw the line that goes between them, and there you go. Right? That's the graph of this inequality. Compound inequality, because there's two different ones here. Okay, now, strictly speaking, X greater than 5, let's say, for another example, is any number that's greater than 5. Okay, what we're doing is we're visualizing it based on the line graph, right? So the graph really is a visualization of the possible solutions to this inequality. It's not the whole thing. It's just anything that's inside of here. But let's say that we want it to be all of the numbers that are being highlighted here, right? Then what we're talking about is not just a solution, but a solution set, right? It's a set that contains literally every number that's bigger than 5. So all of that stuff in there. If we wanted to notate a set, a solution set, and not just say this and have it have, some solution, right? I could 7 is an answer, right, to that thing. But what if I want it to be every number, right, that's bigger than 5? Then what we've got to do is talk about this visualization as a set of numbers, okay? And the way to do that is to use something called set builder notation. And it's kind of confusing at first, but it's just a simple application that makes it interpret it as a set instead of just a standalone inequality that has any solution that's bigger than 5. Now it'll have all the solutions, right, that are bigger than 5. And that's really the difference. If someone just says this, pick a number bigger than 5, and then you win. You've solved the inequality. But what if someone says, no, I want you to find all of the solutions? Okay, you can't just say this anymore, right? That's not signifying all the solutions. So this is set builder notation. And the first thing to point out is that these little curly brackety thingies, those signify that you're talking about a set. And a set, very simply, we're not going to get into set theory or anything here, is a container. It's something that has stuff in it. I always think about it as like a lunchbox. So there's stuff inside of a lunchbox. All those things are called elements of your set. Okay, but it's just a container. It has stuff inside of it. X is typically used as the variable, but you could use whatever you want. It could be A, it could be B. Typically, that in higher level math classes, this might have a specific form. So if you're talking about sets that contain only even numbers, then maybe you've got 2x there, and each of those things is of the form 2x. But for the basic definition, we'll always just use an x or an a or a y or a b or whatever the variable is. So that's just what a standard element in the set looks like. This bar is actually a notation for reading such that. And then you've got your condition on x. And our condition on x is that it's bigger than 5. And that is it. That's the set builder notation. So really, if you wanted to really simplify this, all you're doing is you're adding these bits around x greater than 5. And now you're talking about a set that contains literally every single number that's bigger than 5. So, 25.7 is in that set. 5.001 is in that set. 15 million, right, is in that set. Anything that's bigger than 5 is going to be in that set. It's a set now, so now you've got infinite things inside of this set. So now it's truly the graph of this thing, right? This is not a visualization anymore. I mean, it is, but it's explicitly defining what your solution set entails. Not just, an answer is somewhere in here. It's saying, no, these are the answers. All the stuff that are inside this green line. Okay, so here's another just quick example. If I wanted to visualize the solution set A such that -1 less than or equal to A less than or equal to 1, 13 rather, excuse me, then we've got our lower bound of -1, it includes it. We've got our upper bound of 13, it includes it. So it's just the line that goes between those two things. Okay? Now, I know you're probably thinking, okay, that's cool. We just add these little bits to notate a set, but that's still kind of annoying to write. But I've got good news for you. There's an easier way, right, to notate a set of numbers, right, to notate a whole bunch of stuff, and it's called an interval. An interval notation basically looks like this. Now, I know you're probably like, what the heck is this about? But effectively, you've got your lower bound and your upper bound, and it has to go in that order, right? And so this is essentially what we're visualizing here is you've got A, some inequality X, some inequality B, right? And the inequality is what's going inside of this kind of dotted line here. So you could use square brackets or parentheses, right? It really depends. You'd use parentheses in this case, and you'd use a square bracket in this case. And in fact, if I wanted to turn this inequality into an interval, I'd have this. Open parentheses here because it does not include the lower bound, and a bracket here because it does include its upper bound. Okay, that's it. That's interval notation. It's really easy to use once you get the hang of it, but obviously let's do some examples here. But it depends on whether or not the boundary value is part of the set or not. That really determines whether you should be using a bracket or a parentheses, and which again is based on the inequality. These two things are parentheses, right? And then these two things are brackets. Whoops. That's a less than or equal to, and then you got a greater than or equal to. So in this case, you're using parentheses. In this case, you're using a bracket. Those kind of look the same, but that's a bracket. Pretend that's a squared off there. Okay, so let's do some quick examples, right? If I want to turn this thing into an interval, I would use an open parentheses on -3, its lower bound, and a bracket on its upper bound because it could include it. That's it. For this one, x is between 0 and 10 both inclusively, so both boundaries get a square bracket, right? Because it's got the less than or equal to in both cases. That corresponds to square bracket, whereas just a less than would correspond to an open parentheses. Now here's an interesting one. Only a lower bound, right? No upper bound. It does include the lower bound, though. So if we're going to visualize this thing, our solution set kind of looks like this. How do we turn that into an interval, right? What is its upper bound if it doesn't have one, right? No upper bound. Well, in that case, you use infinity. Okay, now the question, of course, is do we use an open parentheses or a bracket at the end of the infinity? But think about it, right? Infinity is not a number. Infinity is a concept, right? It means it goes on forever. You can always pick a bigger number. So can you ever be equal to infinity? No. If you can't be equal to the upper bound, then you're going to use a parentheses. You're not going to ever use a bracket for an infinity. Okay, here's another one. This one has no lower bound. Take a second, see if you could do that one. X less than -11. How would we write that as an interval? It's got an upper bound. It can't be equal to the upper bound. But then what should we put as its lower bound? All right, and if you said -infinity, then you'd be right. -infinity is the lower bound because there isn't one. And then -11 is the upper bound. Cannot be -11. Cannot be -infinity, so both of them end up being parentheses. Okay, it's also easier to graph in this situation as well. And I think I just did like one example. Yeah. Okay, so this one's interesting because I put a huge amount of space between these two things. So actually, here's my number line. Actually, here's the solution. Here's just the whole thing. Let me explain. So I put each of these tick marks represents a distance of 10. So I did -10, 0, 10. And so I started my number line at -10, but then it ended at 300. And traditionally, when your boundary is not explicitly on the number line, like it's not 100 or 10 or 20 or any or anything like that, then you have to notate it, right? So I put -3 right here. That's the lower bound. It's filled. It can be the lower bound. And then 250, I didn't necessarily need to put this since 250 is an actual tick mark there, but I think it's just nice to notate, oh, hey, here's 250. Put the circle there and then put the line between them. Oh, see? I knew I was going to do this. If your book would write square brackets instead. But again, that's kind of personal preference. You could use square brackets. You could use closed-in circles to represent this. I think the one of the nice things, and this goes in the pro column for square brackets. It's the same notation that you use for intervals, right? So you just kind of stick it on there on the visualization as well. All right, that is basically it. You can pause this. This is like literally every type of interval that you'd see, where the left boundary is, the lower boundary, I should say, is open. The right boundary is open, meaning that it's not equal to. The x cannot be the upper or lower boundaries in the first one. The second one, x can be the lower boundary, but it can't be the upper. So this is just kind of all the possible combinations, if you will, of intervals, and I put the set builder notation and how it corresponds to the interval notation, and then how to notate those things, how to visualize them on the graph in both notations. So the line in red is the kind of my personal preference. I like the circles and closed circles, and then the ones in blue are the way that your book does it. Okay, you'll notice the very last one doesn't have a blue one because you notate them the same. The entire number line is just all real numbers. And it does have an interval notation. It's -infinity to +infinity. All right, so a little longer of a video. I actually did not intend it to be this long, but there is some nuance with teaching this stuff. So hopefully that was helpful. If you guys have any questions, please make sure that you use Piazza or send me an email. And I'll see you guys in the next one. So yeah.